In the silent vacuum of space, 8 worlds trace invisible paths through the darkness around a burning star, each moving at precisely the speed required to neither fall nor escape. Mercury races through like it's a sprint, while Neptune drifts through a journey spanning human lifetimes. These aren't random wanderings. Behind these orbital periods lies a cosmic speed limit that determines whether worlds survive or perish. Why does Mercury's year pass in weeks while Neptune requires nearly 2 centuries? And what invisible mathematics governs these cosmic rhythms? If you find wonder in the mechanics of the universe, a like and subscribe helps us continue exploring these celestial mysteries together. Tonight, the cosmic clockwork awaits, and every orbital period reveals something profound about the universe we inhabit. Let's begin. The closest planet to our star completes its journey around the Sun in just 88 Earth days, making it the solar system's speed champion. Mercury hurtles through space at nearly 50 kilometers per second, covering the distance around its elliptical path faster than any other world in our planetary family. This breakneck pace isn't optional, but necessary for survival at such a close distance to the Sun's gravitational grip. The planet's proximity to our star means it must move extraordinarily fast to avoid being pulled inward, creating a perpetual sprint that has continued for over 4 billion years. To put this velocity in perspective, Mercury moves roughly 140 times faster than a commercial airliner. If you could somehow stand on Mercury's surface and perceive the stars moving overhead, you would witness the entire zodiac sweep across your sky in less than 3 Earth months. The planet's year passes in what we would consider a single season, completing 4 full orbits around the Sun in the time Earth experiences one. Yet Mercury's relationship with time holds a peculiar twist that makes its calendar unlike any other world. While the planet races around the Sun every 88 days, it rotates on its axis much more slowly, taking 59 Earth days to complete a single rotation. This creates a strange synchronization where Mercury completes exactly 3 rotations for every 2 orbits. A gravitational lock that produces one of the solar system's most unusual day-night cycles. The result is a solar day on Mercury that lasts 176 Earth days, twice as long as its year. If you watch the Sun from Mercury's scorched surface, you would see it rise, crawl across the sky with agonizing slowness, set, and then rise again, all while the planet completed 2 full journeys around our star. In some locations on Mercury, the Sun appears to rise part-way, reverse direction, and set again, then rise once more, creating a celestial dance visible nowhere else in our cosmic neighborhood. This rapid orbital period made Mercury challenging for ancient astronomers to observe and understand. The planet never strays far from the Sun in Earth's sky, visible only during brief windows at dawn or dusk when it emerges from the solar glare. Ancient civilizations sometimes mistook Mercury's morning and evening appearances for 2 different objects, not realizing they were watching the same swift world racing around the Sun. Mercury's 88-day year represents the fundamental relationship between proximity and velocity that governs all orbital motion. The closer a world sits to the Sun's gravitational center, the faster it must travel to maintain stable orbit. This principle, emerging from the mathematics of gravity and motion, dictates that inner planets sprint while outer worlds drift, creating the spectrum of orbital periods we observe throughout our solar system. As we move outward from Mercury's swift circuit, we encounter worlds that gradually slow their pace, each marking time according to its distance from our star. There's an elegant relationship between how far a planet sits from the Sun and how fast it must travel to maintain its orbit. This mathematical connection, discovered through centuries of careful observation, reveals that closer planets must race while distant worlds can drift more leisurely through space. The formula governing orbital velocity shows that speed decreases with the square root of distance, creating a cosmic pattern where inner planets complete their years in weeks, while outer giants require decades or centuries. Understanding this relationship transforms orbital periods from random numbers into predictable consequences of physical law. The mathematics underlying this pattern emerges from the balance between gravitational attraction and orbital motion. A planet closer to the Sun experiences stronger gravitational pull, requiring higher velocity to avoid spiraling inward. As distance increases, gravitational force weakens, allowing planets to maintain stable orbits while moving more slowly through space. This inverse relationship between distance and required velocity creates the orderly progression of orbital periods we observe from Mercury to Neptune. Consider the dramatic difference between neighboring worlds. Mercury, orbiting at an average distance of 58 million kilometers from the Sun, must maintain its 4.7 km per second velocity to complete its 88-day orbit. Venus, positioned at 108 million kilometers, travels at 35 kilometers per second and requires 225 days. Earth, at 150 million kilometers, moves at 30 kilometers per second through its 365-day journey. Each step outward brings a notable decrease in velocity and a corresponding increase in orbital period. This pattern continues with mathematical precision as we venture toward the outer solar system. Mars travels at 24 kilometers per second, Jupiter at 13, Saturn at 9.7, Uranus at 6.8, and Neptune at just 5.4 kilometers per second. The numbers aren't random but follow predictable mathematical relationships that astronomers can express in precise equations. These formulas allow us to calculate the orbital period of any object if we know its distance from the Sun, or conversely, to determine its distance if we can measure how long it takes to complete one orbit. The elegance of these relationships reveals something profound about the universe. Physical laws operate with consistency across vast scales of space and time, creating patterns that human mathematics can describe and predict. The same gravitational principles that make an apple fall on Earth govern the motion of worlds billions of kilometers away, demonstrating a fundamental unity in how nature operates. This mathematical predictability transforms astronomy from mere observation into a science capable of forecasting cosmic events with extraordinary accuracy. Astronomers can predict planetary positions years or centuries in advance, calculating when worlds will align or when they'll reach specific points in their orbits. The reliability of these predictions confirms that we've uncovered genuine principles governing celestial motion, rather than imposing arbitrary patterns on random phenomena. As we continue our journey outward from the Sun, we'll see these mathematical principles manifest in the actual orbit. Venus completes her journey around the Sun in 225 Earth days, but her relationship with time holds peculiarities that have puzzled astronomers for generations. This cloud-shrouded world moves through space at about 35 kilometers per second, slower than Mercury, but still remarkably swift by human standards. What makes Venus truly strange is that her day lasts longer than her year, rotating so slowly on her axis that the Sun rises and sets less frequently than her orbital completions. This temporal paradox creates a world where stellar motion and planetary motion exist in an almost dreamlike relationship. Venus takes 243 Earth days to complete a single rotation on its axis, meaning its day exceeds its year by 18 Earth days. This sluggish spin makes Venus the slowest rotating planet in our solar system, turning so gradually that you could walk across its surface faster than it rotates beneath you. If you could survive the crushing atmospheric pressure and scorching temperatures, you could theoretically outpace the planet's rotation by strolling at a leisurely walking speed. The strangeness deepens when you consider the direction of Venus's rotation. While most planets spin counterclockwise when viewed from above their north poles, Venus rotates clockwise, the opposite direction from nearly every other world in our solar system. Only Uranus shares this retrograde rotation, though its extreme axial tilt makes the comparison less direct. Venus spins backward, a cosmic rebel turning against the grain of the solar system's general rotation. What caused this peculiar motion remains uncertain, Scientists theorize that Venus may have experienced a massive collision early in its history, an impact so catastrophic it reversed or drastically slowed the planet's original rotation. Alternatively, gravitational interactions between Venus's dense atmosphere and the Sun's tidal forces might have gradually slowed and reversed its spin over billions of years. The truth likely lies buried in the planet's ancient past, hidden beneath clouds of sulfuric acid that permanently obscure the surface from direct observation. The combination of Venus's orbital period and rotation creates an unusual solar day measuring 117 Earth days from one sunrise to the next. Because the planet rotates backward relative to its orbital motion, the Sun appears to rise in the west and set in the east, opposite to Earth's familiar pattern. This westward sunrise occurs only twice during each Venusian year, creating a calendar where seasons and days interweave in ratios alien to human experience. Ancient astronomers recognized Venus as the brightest object in the night sky after the Moon, tracking its appearances with reverence and fascination. Many civilizations identified Venus with deities of love and beauty, unaware that behind its brilliant appearance lay a world of extreme temperatures and crushing atmospheric pressure. The planet's 225-day orbital period made it a reliable timekeeper, its predictable movements across dawn and dusk skies marking the passage of months with celestial precision. As we move from Venus's backward-spinning mystery toward Earth, we encounter the world whose orbital period defines our fundamental experience of time. Our home world traces its path around the Sun in exactly 365.25 days, a period that has defined human civilization's relationship with time itself. Earth travels at approximately 30 kilometers per second, fast enough to maintain orbital stability while remaining in the habitable zone where liquid water can exist on planetary surfaces. This orbital period creates the seasonal cycles that have shaped life's evolution over billions of years. From the timing of plant blooms to the migration patterns of animals, the precision of Earth's year reminds us that we're passengers on a cosmic vessel moving through space at speeds our minds struggle to comprehend. That extra quarter day beyond 365 full days creates the necessity for leap years, a correction ancient civilizations recognized through careful astronomical observation. Without adding an extra day every 4 years, our calendar would gradually drift out of alignment with the seasons, eventually placing winter in what we currently call summer months. The Roman Emperor Julius Caesar implemented the leap year system in 45 BCE. Though it required further refinement centuries later, when Pope Gregory XIII adjusted the calendar to its current form, skipping leap years in most century years to maintain even more precise alignment. Earth's 365-day journey positions us neither too close to the Sun's blazing heat nor too far into the frozen outer darkness. This orbital distance of approximately 150 million kilometers, often called an astronomical unit, places our world in the habitable zone, where temperatures allow water to exist as liquid rather than permanently frozen ice or boiled away vapor. This positioning isn't just convenient but essential for the existence of life as we know it, creating conditions stable enough for complex chemistry to flourish over geological time. The tilt of Earth's axis relative to its orbital plane creates the seasons we experience as our world circles the Sun. During one portion of the orbit, the northern hemisphere tilts toward the Sun, receiving more direct sunlight and experiencing summer while the southern hemisphere endures winter. 6 months later, the situation reverses as Earth reaches the opposite side of its orbit. This annual cycle has operated with extraordinary consistency throughout Earth's history, providing the reliable environmental rhythms that allowed life to adapt and diversify. Consider the speed at which we're moving as you rest tonight. Earth races through space at 30 kilometers every second, covering 108,000 kilometers every hour. In the time it takes to read this sentence, our planet has traveled hundreds of kilometers along its orbital path, yet we feel no motion, no cosmic wind, no sense of the extraordinary velocity at which we're perpetually falling around the Sun. This stability, this precise 365-day rhythm, has persisted for billions of years. The same orbital period that governs our modern calendar also governed the days of the dinosaurs, the epochs when the first life emerged from ancient oceans, and the eons before life existed at all. Earth has circled the Sun approximately 4.5 billion times since the solar system formed, each orbit lasting the same duration, creating a cosmic metronome that has measured time since before time had meaning. Understanding why planets orbit, rather than fly away or crash into the Sun, requires grasping how gravity operates across the vast emptiness of space. The Sun's massive bulk creates a gravitational field that reaches across billions of kilometers, pulling on each planet with invisible force. This attraction would normally draw planets inward toward destruction, but their sideways motion creates a perpetual falling that never quite reaches the Sun. Think of it like swinging a ball on a string. The tension pulls inward, while the ball's motion keeps it moving in circles, creating stable orbital paths that can persist for geological epochs. Isaac Newton first recognized this principle in the 1680s when he realized that the same force pulling apples toward Earth also governs the motion of the Moon and planets. He understood that the Moon is constantly falling toward Earth, but moving sideways fast enough that it continuously misses our planet, tracing a circular path that never intersects the ground. This insight revolutionized astronomy, revealing that celestial mechanics follow the same physical laws that govern everyday objects. The balance between gravitational attraction and sideways velocity determines whether an object will orbit, escape, or collide. Too much sideways velocity and the planet flies away into interstellar space, escaping the Sun's gravitational embrace entirely. Too little velocity and the planet spirals inward, eventually plunging into the Sun's blazing surface. The orbital velocities we observe represent the precise speeds required to maintain stable, circular or elliptical paths. This gravitational tether operates without physical connection, reaching across empty space through a mechanism that still captivates physicists. Einstein later refined our understanding, showing that gravity results from massive objects curving the fabric of spacetime itself. The Sun creates a depression in spacetime, and planets follow the curved paths created by this warping of reality's geometric structure. Rather than thinking of gravity as a force pulling objects together, Einstein taught us to see it as objects following the straightest possible paths through curved space. The strength of gravitational attraction decreases with distance, following an inverse square law. Double the distance from the Sun, and gravitational pull becomes 4 times weaker. Triple the distance, and it weakens by a factor of 9. This mathematical relationship explains why outer planets need less velocity to maintain their orbits. They experience weaker gravitational pull and therefore require less speed to avoid falling inward. Despite gravity's weakening with distance, the Sun's influence extends remarkably far. Even Neptune, nearly 4.5 billion kilometers from the Sun, remains firmly bound by solar gravity, held in an orbit it has traced for billions of years. Beyond Neptune, in the distant Oort cloud, objects may orbit at distances approaching a light year from the Sun, barely held by gravitational threads stretching across vast cosmic distances. This gravitational architecture creates the stable solar system we inhabit, where worlds maintain their orbits with extraordinary reliability, circling the Sun in paths that have remained essentially unchanged throughout human history and will persist far into the future. Mars completes its orbit around the Sun in 687 Earth days, roughly twice as long as our own year. This rust-colored world travels at about 24 kilometers per second, noticeably slower than the inner planets due to its greater distance from the Sun's gravitational center. Ancient astronomers noticed that Mars appeared to move backward across the sky during certain periods, an apparent retrograde motion caused by Earth overtaking the slower-moving red planet during their respective orbital journeys. Understanding Mars's orbital period was crucial to early astronomers, who used these calculations to develop models of how the solar system actually operates. The retrograde motion of Mars puzzled astronomers for centuries, appearing to violate the orderly progression they observed in other celestial objects. For weeks at a time, Mars would reverse its eastward drift across the constellations, moving westward before resuming its normal path. This apparent backward motion created complex loops when plotted against the background stars, patterns that ancient astronomers struggled to explain using Earth-centered models of the cosmos. The solution required recognizing that Earth orbits closer to the Sun and therefore moves faster than Mars. As Earth overtakes the red planet during our respective journeys around the Sun, Mars appears to move backward against the distant stars. Much like a faster car on a highway makes a slower vehicle appear to drift backward relative to distant landscape features. This explanation only made sense once astronomers accepted that Earth itself orbits the Sun rather than remaining stationary at the center of creation. Mars's 687-day year creates seasonal patterns remarkably similar to Earth's, though stretched across nearly 2 Earth years. The planet's axial tilt of 25 degrees closely matches Earth's 23.5-degree tilt, producing familiar seasonal variations as different hemispheres tilt toward and away from the Sun during the orbital journey. Northern Hemisphere spring on Mars lasts approximately 194 Martian days, summer 178 days, autumn 142 days, and winter 154 days, each season nearly twice as long as its earthly counterpart. These extended seasons create dramatic changes visible even through Earth-based telescopes. Mars's polar ice caps, composed of frozen carbon dioxide and water ice, advance and retreat with the seasons, growing during winter and shrinking during summer. Dust storms sweep across the planet's surface, sometimes engulfing the entire world in rusty clouds that can persist for months. The longer seasonal cycle allows these weather patterns to develop more fully than they could on Earth, creating atmospheric dynamics that operate on extended timescales. Ancient civilizations tracked Mars with particular attention, noting its reddish color and associating it with war and conflict. The Romans named it after their god of war, while the Greeks called it Ares. These cultures didn't understand that Mars's distinctive color comes from iron oxide covering its surface, rust on a planetary scale created by ancient interactions between iron-rich rocks and the thin atmosphere. As Mars marks the boundary of the inner solar system, we prepare to cross a threshold where rocky worlds give way to realms of gas giants and frozen distances. Between Mars and Jupiter lies a region where millions of rocky fragments trace their own paths around the Sun, each with orbital periods typically ranging from 3 to 6 years. This asteroid belt represents a transition zone in our solar system, where the architecture shifts from small rocky worlds to massive gas giants. The asteroids within this belt move at speeds determined by their individual distances from the Sun, creating a complex traffic pattern of celestial debris. Some asteroids complete their orbits in neat resonances with Jupiter's 12-year period, cleared into gaps by gravitational interactions that have operated for billions of years. These gaps, called Kirkwood gaps after their discoverer Daniel Kirkwood, appear at specific distances where an asteroid's orbital period would create simple mathematical ratios with Jupiter's orbit. An asteroid orbiting at a distance where it completes exactly 3 orbits for every one of Jupiter's, or 4 orbits for every 2 of Jupiter's, experiences repeated gravitational tugs at the same point in its orbit. Over millions of years, these repeated interactions nudge asteroids out of these resonant zones, creating empty bands within the otherwise populated belt. The asteroid belt isn't the dense field of colliding rocks portrayed in science fiction. These millions of objects spread across such vast distances that you could fly through the belt without ever coming close to hitting anything. The total mass of all asteroids combined equals less than 5% of the Moon's mass, scattered across a ring hundreds of millions of kilometers wide. Most asteroids orbit peacefully for billions of years without encountering another object. Solitary voyagers tracing elliptical paths in the darkness between worlds. Ceres, the largest object in the asteroid belt, completes its orbit in 4.6 Earth years, moving at approximately 17.9 kilometers per second. This dwarf planet contains roughly a third of the entire belt's mass, large enough that gravity has pulled it into a spherical shape. Smaller asteroids follow similar paths at varying distances, each obeying the same gravitational mathematics that governs planetary motion, though on a reduced scale. The existence of the asteroid belt between Mars and Jupiter suggests that planet formation was disrupted in this region. Jupiter's immense gravitational influence prevented these rocky fragments from coalescing into a single planet, stirring up their orbits and causing collisions that shattered larger protoplanets rather than allowing them to grow. The belt represents a planetary formation process that never completed, frozen in an intermediate stage by Jupiter's gravitational dominance. Some asteroids follow orbits that cross into the inner solar system, becoming potential threats to Earth as their paths intersect our own. These near-Earth asteroids complete their orbits in periods ranging from a few months to several years, periodically passing close to our world during their elliptical journeys. Astronomers carefully track these objects, calculating their orbital periods with precision to predict when and where they'll appear in Earth's neighborhood. As we cross this boundary of rocky fragments, we prepare to encounter worlds of an entirely different nature, gas giants whose masses dwarf everything we've encountered so far in our outward journey. The solar system's largest planet requires nearly 12 Earth years to complete a single orbit around the Sun, moving at approximately 13 kilometers per second through space. Jupiter's immense bulk makes it a gravitational powerhouse that influences the orbits of countless smaller objects throughout the solar system. Ancient astronomers tracked Jupiter's slow progression across the celestial sphere, watching it move through the zodiac constellations over the course of a human generation. This orbital period made Jupiter significant in ancient astrology and astronomy, as civilizations could measure their histories by the giant planet's stately march across the night sky. The precise orbital period measures 11.86 Earth years, meaning Jupiter returns to nearly the same position against the background stars roughly every dozen years. A child born when Jupiter occupies one constellation will see it return to that same region of sky as they approach adolescence. Then again, as they enter their mid-20s, creating a celestial marker for the passage of human life stages. This connection between Jupiter's orbital rhythm and human development made the planet significant in various cultural traditions. Its position at birth thought to influence personality and destiny. Jupiter's mass exceeds that of all other planets combined, containing more than twice the matter found in Saturn, Uranus, Neptune, and all the rocky inner worlds added together. This enormous mass, roughly 318 times Earth's, makes Jupiter's gravitational influence felt throughout the solar system. The planet acts as a cosmic shepherd, its gravity deflecting comets and asteroids that might otherwise threaten the inner planets, possibly protecting Earth from impacts that could have prevented life's emergence or caused mass extinctions. The transition from Mars's 687-day orbit to Jupiter's 4,333-day journey represents a dramatic shift in the solar system's architecture. We've moved from terrestrial worlds of rock and metal to gas giants composed primarily of hydrogen and helium, from planets you could theoretically stand on to worlds with no solid surface at all. Jupiter's cloud tops, visible through telescopes as colourful bands and swirls, mark the uppermost layer of an atmosphere that extends thousands of kilometers deep before gradually transitioning to liquid and metallic hydrogen under crushing pressure. Jupiter's orbital distance from the Sun averages about 778 million kilometers, more than 5 times Earth's distance. At this remove, sunlight arrives 27 times dimmer than on Earth, and temperatures plunge to minus 145 degrees Celsius in the upper atmosphere. Yet Jupiter radiates more heat than it receives from the Sun, its interior still warm from the planet's formation billions of years ago, slowly cooling while emitting infrared radiation into space. The planet's family of moons orbits Jupiter while the entire system circles the Sun, creating nested cycles of motion. The 4 largest moons, discovered by Galileo in 1610, orbit Jupiter with periods ranging from 1.8 days for Io to 16.7 days for Callisto. Their regular rhythms, creating eclipse patterns that early astronomers used to make precise measurements of time and planetary motion. While distance from the Sun primarily determines orbital period, a planet's own mass also plays a subtle but important role in the cosmic dance. Massive planets like Jupiter actually cause the Sun itself to wobble slightly, as both objects orbit around a common center of mass called the barycenter. This gravitational interaction means that Jupiter and the Sun are technically orbiting each other, though the Sun's massive bulk keeps this point very close to its surface. Understanding how mass affects orbital mechanics reveals that the solar system operates more like a complex gravitational ballet than a simple system of objects circling a stationary center. The barycenter between the Sun and Jupiter lies just above the Sun's surface, approximately 743,000 kilometers from the solar center. This placement means that as Jupiter completes its 12-year orbit, the Sun traces a small circle in space, wobbling around this common gravitational balance point. The motion is subtle from our perspective, shifting the Sun's position by about 1 solar radius. But sensitive instruments can detect this wobble by measuring slight shifts in the wavelengths of sunlight, revealing the periodic tug of Jupiter's gravity. This principle of mutual gravitational influence applies to every planet, though smaller worlds create barycenters so close to the Sun's center that their effect becomes negligible. Earth's barycenter with the Sun lies deep within the solar interior, only about 450 kilometers from the Sun's center. Yet, the principle remains the same for all objects. From the smallest asteroid to the most massive planet, each pulling on the Sun while the Sun pulls back. Astronomers use this wobble technique to discover planets around distant stars, detecting the rhythmic motion of stars as unseen planets orbit around them. The wobble's period reveals the orbital period of the planet, while the amplitude of the motion indicates the planet's mass. This method, called radial velocity detection, has discovered thousands of exoplanets by observing stellar wobbles too subtle for direct visual detection, but clear in spectroscopic measurements. The combined gravitational influences of all the planets create a complex wobble in the Sun's motion, a composite effect of multiple masses pulling from different directions as they move through their respective orbits. Computer models tracking these interactions can predict the Sun's precise position decades or centuries into the future, accounting for every gravitational tug from every significant mass in the solar system. This mutual influence extends beyond simple position, affecting orbital stability over long timescales. Planets gravitationally interact with each other, creating subtle perturbations that accumulate over millions of years. Jupiter's mass makes it the dominant influence on other planets' orbits, its gravity nudging asteroids, deflecting comets, and creating the resonances we observe throughout the solar system. Understanding these mass-dependent interactions reveals that no planet truly orbits in isolation, but participates in a gravitational symphony, where every object influences every other object across the vast distances of space. Saturn glides through its orbital path in approximately 29.5 Earth years, moving at about 9.7 kilometers per second through the outer solar system. This ringed giant's stately journey means that humans who witness Saturn in one position as children will see it occupy the opposite side of the Sun as adults. The planet's magnificent ring system travels along with Saturn on this decades-long circuit, maintaining its orientation relative to the distant stars. Ancient observers who tracked Saturn's motion thought they were watching a divine wanderer, unaware they were measuring a physical process governed by gravitational mathematics that operates with clockwork precision. The rings, composed of countless ice particles ranging from dust grain size to house-sized chunks, maintain their flat plane as Saturn orbits. From Earth, we see the rings from varying angles as our world and Saturn move through their respective orbits. Sometimes we view the rings edge-on, when they nearly disappear from view despite spanning more than 280,000 kilometers across. Other times we see them tilted at their maximum angle, displaying their full magnificent breadth. This changing perspective creates a cycle within Saturn's longer orbital cycle, a visual rhythm that repeats roughly every 15 years as Earth and Saturn's positions shift relative to each other. Saturn orbits the Sun at an average distance of 1.4 billion kilometers, nearly 10 times farther than Earth. At this immense distance, sunlight takes about 80 minutes to reach Saturn's cloud tops, arriving so diminished that the Sun appears 100 times dimmer than we see it from Earth. The reduced solar energy creates frigid conditions in Saturn's upper atmosphere, with temperatures plunging to minus 178 degrees Celsius, cold enough to freeze nitrogen solid. Ancient astronomers considered Saturn the most distant planet known, the edge of the known cosmos, beyond which no worlds wandered. The Greeks named it after Kronos, the Titan of time, while Romans called it Saturn, recognizing in its slow, celestial progression a symbol of age and the measured passage of years. These civilizations tracked Saturn's position for centuries, building tables of its motion that allowed them to predict where the planet would appear decades in advance. Saturn's 29.5-year orbit creates seasons that last more than 7 Earth years each. The planet's axial tilt of 26.7 degrees, similar to Earth's, means that different hemispheres receive varying amounts of sunlight as Saturn circles the Sun. During Saturn's northern hemisphere summer, that pole tilts toward the Sun for more than 7 years of continuous sunlight, while the southern hemisphere endures an equally long winter. Then the pattern reverses as Saturn continues its journey, bringing summer to the south and winter to the north. The lengthy seasons create atmospheric patterns that persist and evolve over years. Massive storms develop in Saturn's atmosphere, some growing large enough to encircle the entire planet, driven by the seasonal heating cycles that operate on timescales far longer than Earth's weather patterns. In the early 1600s, Johannes Kepler discovered 3 mathematical laws that describe exactly how planets move through space, transforming astronomy from observation into prediction. His first law revealed that orbits are ellipses rather than perfect circles, with the Sun positioned at one focus of each elliptical path. The second law showed that planets sweep out equal areas in equal times, meaning they move faster when closer to the Sun and slower when farther away. His third law established the mathematical relationship between orbital period and distance, proving that orbital time increases with the 3/2 power of the semi-major axis. Kepler arrived at these laws through painstaking analysis of astronomical observations recorded by Tycho Brahe, the most precise naked-eye observer in history. For years, Kepler struggled to fit Tycho's Mars observations into circular orbits, trying countless combinations of circles and speeds that all failed to match the actual positions recorded in Tycho's meticulous tables. The breakthrough came when Kepler abandoned the ancient assumption that celestial motion must follow perfect circles, allowing himself to consider elliptical paths instead. The ellipse solved the problem elegantly. Mars's orbit, like all planetary orbits, traces an ellipse with the Sun positioned not at the center, but at one of the 2 focal points. This placement means that Mars's distance from the Sun varies throughout its orbit, sometimes closer and sometimes farther, creating the subtle position changes that had frustrated circular models. The other focal point remains empty, a mathematical abstraction with no physical object occupying it. Kepler's second law emerges from a principle of conservation, showing that planets move faster when closer to the Sun and slower when farther away. Imagine drawing a line from the Sun to a planet, then watching how much area that line sweeps across as the planet moves. Kepler discovered that this swept area remains constant over equal time intervals, regardless of where the planet sits in its orbit. During the portion of orbit when a planet passes close to the Sun, it must move quickly to sweep out the same area that it covers more slowly during the distant portion of its elliptical path. The third law provides the mathematical key to understanding orbital periods. Kepler found that if you cube a planet's average distance from the Sun and divide by the square of its orbital period, you get the same number for every planet. This relationship meant that knowing either a planet's distance or its orbital period allowed astronomers to calculate the other value with precision. The law revealed a hidden harmony in planetary motion, a mathematical relationship suggesting that some fundamental principle governed all orbital motion. Kepler didn't understand why his laws worked. He described the patterns, but couldn't explain the underlying mechanism that created them. That explanation would wait for Isaac Newton, who would show decades later that Kepler's laws emerged naturally from universal gravitation and the mathematics of motion. Newton proved that Kepler had discovered consequences of deeper physical principles, patterns that must appear whenever objects orbit under gravitational influence. These three laws remain fundamental to astronomy, used daily by scientists calculating orbital periods for newly discovered exoplanets or predicting the positions of solar system objects centuries into the future. No planet follows a perfectly circular path around the Sun, instead tracing elliptical routes that bring them alternately closer and farther from our star. Earth's orbit, while nearly circular, still varies by about 5 million kilometers between perihelion and aphelion, the closest and farthest points. This elliptical nature affects orbital speed throughout the year, with planets moving slightly faster during the portion of their orbit when they're nearest the Sun. Understanding orbital ellipticity reveals why some planets experience more dramatic seasonal variations and why predicting exact positions requires sophisticated mathematical calculations rather than simple circular motion assumptions. An ellipse resembles a stretched circle, defined by two focal points rather than a single center. The sum of distances from any point on the ellipse to both foci remains constant, creating the characteristic oval shape. For planetary orbits, the Sun occupies one focus while the other remains empty, a geometric requirement rather than a physical location. The degree of stretching, called eccentricity, measures how much an orbit deviates from perfect circularity, ranging from 0 for a perfect circle to values approaching 1 for highly elongated ellipses. Earth's orbital eccentricity of 0.017 makes our path around the Sun nearly circular, with only subtle variation in solar distance throughout the year. We reach perihelion, our closest approach to the Sun, in early January at about 147 million kilometers. 6 months later, at aphelion in early July, we've drifted to 152 million kilometers. This 5 million kilometer variation affects the amount of solar energy reaching Earth by about 6% between closest and farthest approaches, though the difference remains small enough that axial tilt rather than distance determines our seasons. Other planets display more eccentric orbits. Mercury's eccentricity of 0.205 creates dramatic distance variations, bringing the planet as close as 46 million kilometers to the Sun at perihelion and sending it as far as 70 million kilometers at aphelion. This 4 million kilometer swing means Mercury receives more than twice as much solar energy at perihelion compared to aphelion, creating extreme temperature variations between different portions of its orbit. Mars also follows a notably elliptical path with eccentricity of 0.093, varying between 207 million and 249 million kilometers from the Sun. This ellipticity contributes to Mars's dramatic seasonal variations, particularly affecting the southern hemisphere, which experiences summer during perihelion when solar heating reaches maximum intensity. The combination of axial tilt and orbital eccentricity creates seasonal temperature swings on Mars, far more extreme than Earth experiences. The gas giants display more modest eccentricities. Jupiter's orbit varies by about 76 million kilometers between perihelion and aphelion, while Saturn's changes by roughly 160 million kilometers. These variations remain small percentages of their overall orbital distances, making their paths appear nearly circular despite the absolute distances involved. Orbital eccentricity affects not just distance but velocity. Kepler's second law requires planets to move faster near perihelion and slower near aphelion, creating subtle variations in how quickly planets progress across the sky as viewed from Earth. Uranus requires 84 Earth years to complete its orbit around the Sun, moving at approximately 6.8 kilometers per second through the frigid outer solar system. This ice giant's most peculiar characteristic is its extreme axial tilt, rotating almost on its side relative to its orbital plane. This unusual orientation means that during portions of its orbit, Uranus's poles point nearly directly at the Sun, creating the most extreme seasonal variations of any planet in our solar system. A single season on Uranus lasts roughly 21 Earth years, long enough that the planet's atmospheric dynamics operate on timescales completely alien to human experience. The planet's axial tilt measures 97.8 degrees, meaning Uranus essentially rolls through its orbit rather than spinning upright like most other worlds. During the Uranian summer solstice, one pole points almost directly at the Sun and experiences 42 years of continuous daylight, while the opposite pole endures an equally long period of darkness. As the planet continues its journey, the Sun gradually moves toward the equator, creating a brief spring and autumn before the pattern reverses and the previously dark pole begins its decades-long summer. What caused this extraordinary tilt remains uncertain. The most widely accepted theory suggests that Uranus suffered a massive collision early in its history, an impact with another planet-sized body that knocked the world onto its side. This catastrophic event would have occurred during the chaotic early solar system, when planetary formation was still underway and such violent collisions remained common. The impact's energy would have been sufficient to reorient the entire planet while leaving it intact, creating the unusual configuration we observe today. Uranus orbits at an average distance of 2.9 billion kilometers from the Sun, roughly 19 times farther than Earth. At this remote location, sunlight arrives 400 times dimmer than we experience, taking nearly 3 hours to travel from the Sun to Uranus's cloud tops. The reduced solar energy creates some of the coldest planetary temperatures in the solar system, with atmospheric temperatures dropping to minus 224 degrees Celsius, cold enough to freeze carbon dioxide and methane. The planet's faint blue-green color comes from methane in its atmosphere, which absorbs red light while reflecting blue and green wavelengths. This methane atmosphere extends thousands of kilometers above a mantle of icy water, ammonia, and methane compounds surrounding a rocky core. Unlike the gas giants Jupiter and Saturn, Uranus qualifies as an ice giant, its composition dominated by these frozen volatile substances rather than hydrogen and helium. Ancient astronomers never observed Uranus, its dimness and slow motion making it indistinguishable from stars without telescopic aid. William Herschel discovered the planet in 1781, initially thinking he'd found a comet before calculations of its orbit revealed it as the seventh planet, doubling the known size of the solar system overnight. The outermost major planet requires approximately 165 Earth years to complete a single orbit, moving at about 5.4 kilometers per second through the distant reaches of our solar system. Neptune has completed only one orbit since its discovery in 1846, meaning that no human has lived to see this world return to the same position in its celestial journey. The planet's orbital period reveals the immense scale of our solar system, where worlds can exist so distant that their years span multiple human lifetimes. Neptune's stately progression through space represents the slowest planetary dance in our cosmic neighborhood. Neptune orbits at an average distance of 4.5 billion kilometers from the Sun, roughly 30 times farther than Earth. At this extreme remove, sunlight takes more than 4 hours to reach the planet's cloud tops, arriving so diminished that the Sun provides only about 1,000th the illumination we experience on Earth. From Neptune's perspective, our star appears as merely a very bright point of light, offering negligible warmth to a world where atmospheric temperatures plunge to minus 214 degrees Celsius. The planet's discovery itself represents one of astronomy's greatest mathematical triumphs. Astronomers noticed that Uranus's orbit deviated slightly from predictions, suggesting an unknown planet's gravitational influence was perturbing its path. Using only mathematics and Newton's laws of gravitation, astronomers calculated where this hypothetical planet should be located. When telescopes turned to that region of sky in 1846, Neptune appeared almost exactly where the calculations predicted, a stunning validation of orbital mechanics and gravitational theory. Since that discovery moment, Neptune has traveled through only one complete circuit around the Sun. The planet returned to its discovery position in 2011, marking the first fully observed Neptunian year. Astronomers who witnessed this completion were celebrating an orbital milestone that connected them across 165 years to their predecessors who first spotted the distant world. No astronomer will live to see Neptune complete 2 full observed orbits, as the second won't conclude until 2176. This extraordinarily long orbital period creates unique challenges for planetary science. Seasonal changes on Neptune unfold across 4 decades for each season, far too slowly for any individual researcher to observe a complete seasonal cycle. Weather patterns, atmospheric dynamics, and thermal variations operate on timescales that exceed human careers, requiring multiple generations of astronomers to piece together Neptune's full climatic behavior. The planet's slow drift through space means its position against the background stars changes almost imperceptibly from year to year. Ancient astronomers never observed Neptune because its faintness and glacial motion made it indistinguishable from stars without precise measurements or telescopic magnification. The world remained hidden in plain sight for all of human history until mathematical prediction finally revealed its location. As Neptune marks the boundary of the major planets, we prepare to venture even farther, into realms where orbital periods stretch beyond human lifetimes into the vast temporal scales of centuries and millennia. Beyond Neptune's orbit, dwarf planets like Pluto, Eris, and Makemake trace immense paths through the outer solar system, requiring centuries to complete their journeys. Pluto needs 248 Earth years to orbit the Sun once, while Eris requires approximately 557 years for its distant circuit. These frozen worlds travel through regions of space where the Sun appears as merely a bright star, providing minimal warmth or light. Their orbital periods reveal the vast scale of the solar system's outer regions, where gravitational influence remains but becomes increasingly subtle across billions of kilometers of space. Pluto's 248-year orbit brings it as close as 4.4 billion kilometers to the Sun at perihelion, and sends it as far as 7.3 billion kilometers at aphelion. This eccentric path actually carries Pluto inside Neptune's orbit for about 20 years during each circuit, making it temporarily closer to the Sun than the 8th planet. The two worlds never collide because their orbits remain tilted relative to each other and locked in a gravitational resonance that keeps them separated despite their crossing paths. The discovery of Pluto in 1930 marked humanity's first encounter with objects in the Kuiper Belt, a vast region beyond Neptune containing thousands of icy bodies left over from the solar system's formation. Pluto orbits among these fellow frozen worlds, the largest known member of a population that extends from Neptune's orbit outward to perhaps 50 astronomical units from the Sun. Each of these objects follows its own elliptical path, with orbital periods increasing as distance grows. Eris, slightly more massive than Pluto, travels an extremely elliptical orbit that carries it between 38 and 98 astronomical units from the Sun. Its 557-year period means that Eris has completed less than 5 full orbits since the pyramids of Giza were built. Currently residing near its farthest point from the Sun, Eris won't return to perihelion until the year 2257, long after everyone alive today has passed. Other dwarf planets display similarly extended timescales. Makemake requires 306 years to complete its orbit, while Haumea needs 284 years. These worlds exist in a realm where orbital velocities drop below 5 kilometers per second, barely fast enough to maintain their gravitational bond with the Sun across such immense distances. From their surfaces, if you could stand on them, the Sun would appear as merely the brightest star in the sky. providing illumination comparable to a full moon on Earth. The reclassification of Pluto from planet to dwarf planet in 2006 reflected our growing understanding of the outer solar system's true population. Rather than diminishing Pluto's significance, the discovery of numerous similar objects revealed it as the first known member of a vast population, a pioneer leading us toward understanding the solar system's distant frontier. These dwarf planets mark a transition zone between the realm of major planets and the even more distant Oort cloud, where comets orbit in a spherical shell, potentially extending a light year from the Sun, requiring millions of years to complete single orbits. Every orbit in the solar system actually involves two objects orbiting around a common center of mass, rather than one object simply circling another. For planets orbiting the Sun, this barycenter lies so close to the Sun's center that the effect is negligible, but it still exists as a fundamental truth of gravitational mechanics. Jupiter's massive bulk places its barycenter with the Sun just outside the solar surface, causing our star to wobble noticeably as the giant planet completes its orbit. Understanding barycenters reveals that gravity operates bidirectionally, with every object pulling on every other object throughout the cosmic expanse. The Earth-Moon system provides a familiar example of barycentric motion. While we commonly say the Moon orbits Earth, both bodies actually orbit around their common center of mass, located about 4,700 kilometers from Earth's center. This point lies beneath Earth's surface, roughly 3/4 of the way from our planet's center to its surface. As the Moon completes its 27-day orbit, Earth traces a small circle around this barycenter, a wobble detectable through careful measurement of our planet's position against distant stars. When two objects possess similar masses, their barycenter lies in the space between them, rather than inside either body. Pluto and its largest moon, Charon, demonstrate this arrangement beautifully. Charon's mass equals about 1-8th of Pluto's, large enough that their barycenter sits in empty space between the two worlds. Both Pluto and Charon orbit this point, locked in a gravitational embrace where neither can claim to be the primary body. Astronomers sometimes call this arrangement a binary system rather than a planet-moon relationship. This barycentric principle applies universally throughout the cosmos. Binary stars orbit their common center of mass, sometimes positioned between the stars, sometimes inside the larger star, depending on their mass ratio. Even galaxies orbit around barycenters when they interact gravitationally, dancing around invisible points defined purely by the distribution of mass. The barycenter concept helps explain why orbital periods remain so stable. Both objects in an orbiting pair must complete their circuits around the barycenter in exactly the same time, maintaining synchronized motion through space. Jupiter and the Sun both complete their barycentric orbits in 11.86 years, Jupiter tracing a vast ellipse while the Sun wobbles through a much smaller path around the point just outside its surface. Understanding barycenters changes how we conceptualize orbits. Rather than imagining smaller objects circling larger stationary bodies, we recognize that all objects participate in mutual gravitational dances, each pulling on the other while both orbit their shared center of mass. The solar system becomes a complex choreography of objects, moving around countless barycenters, from the Sun-Jupiter pair to Earth-Moon to every asteroid affected by planetary gravity. This mutual motion becomes especially important when detecting exoplanets around distant stars. Astronomers watch for the telltale wobble of stars as unseen planets pull them around shared barycenters, revealing planetary masses and orbital periods through the rhythm of stellar motion. Determining how long a planet takes to orbit the Sun requires careful observation over extended time periods. Tracking positions against the background stars, ancient astronomers used naked eye observations, noting when planets return to the same position relative to distant constellations. Modern astronomers employ sophisticated instruments that can measure planetary positions with extraordinary precision, calculating orbital periods to fractions of a second. For nearby planets, These measurements required only years of observation. But for distant Neptune, astronomers needed mathematical predictions before they could confirm the planet's 165-year period through direct observation. The simplest method involves watching a planet until it returns to the same position relative to the background stars, a complete circuit marking one full orbital period. For Mercury, ancient astronomers could measure this cycle in months, watching the swift planet dart around the Sun and return to its starting position against the constellations. Venus required less than a year of observation, Mars just under 2 years. These relatively short periods allowed ancient civilizations to compile accurate tables of planetary motion using nothing more than careful naked-eye observations recorded over decades. The outer planets presented greater challenges. Jupiter's 12-year orbit required patience, forcing astronomers to track the planet across multiple observing seasons and sometimes across entire careers. Saturn's 29-year period meant that a single astronomer might observe less than 2 complete orbits in their lifetime. These extended timescales made it difficult to measure orbital periods with high precision, as small errors in position measurements could accumulate over the decades required for observation. The discovery of Uranus in 1781 created an interesting situation. Astronomers could observe the planet's slow motion across the sky, but its 84-year orbital period meant no one alive at discovery would survive to see it complete even a single orbit. Instead, astronomers used mathematical models based on Kepler's laws, calculating the orbital period from careful measurements of the planet's position over several years. These calculations proved remarkably accurate, predicting Uranus's motion decades before it could be confirmed through direct observation of a complete orbit. Neptune presented an even greater challenge. Discovered in 1846, the planet completed its first observed full orbit since discovery, only in 2011, requiring 165 years for confirmation that spanned multiple human generations. Yet astronomers knew Neptune's orbital period with great precision long before 2011, using mathematical calculations based on positional measurements taken over several decades. Modern techniques have refined orbital period measurements to extraordinary precision. Radar ranging, spacecraft flybys, and gravitational perturbation analysis allow astronomers to determine orbital periods to fractions of a second. Mars's orbital period, for instance, is known to be 686.98 Earth days, a precision that would have astounded ancient observers who could only estimate it to the nearest day or week. The most distant objects require combining direct observation with mathematical modeling. Astronomers track these bodies for years or decades, then use gravitational theory to extrapolate their full orbital paths. Each planet's orbital velocity represents a delicate balance between gravitational attraction and the tendency to continue moving in a straight line. If a planet moved too slowly, it would spiral inward toward the Sun, eventually plunging into our star's blazing surface. If it moved too quickly, it would escape the Sun's gravitational grip entirely, flying away into interstellar space never to return. The actual velocities we observe represent the precise speed needed to maintain stable orbits, speeds that have remained essentially unchanged since the solar system's formation over 4.5 billion years ago. This critical velocity, called orbital velocity, can be calculated for any distance from the Sun using gravitational principles. At Earth's orbital distance, the required velocity equals approximately 30 kilometers per second. Move slightly faster, and Earth's orbit would become more elliptical, carrying us farther from the Sun at aphelion. Move significantly faster, beyond about 42 kilometers per second at Earth's distance, breaking free from solar gravity entirely to wander through the galaxy as a rogue world. The concept of escape velocity becomes crucial when considering how objects can leave one gravitational field for another. Spacecraft launched from Earth must reach 11.2 kilometers per second relative to our planet to escape Earth's gravity, then require additional velocity changes to reach other worlds or escape the solar system entirely. The Voyager spacecraft, humanity's most distant emissaries, achieved the solar system's escape velocity and now drift through interstellar space, having exceeded the speed necessary to remain bound to the Sun. These velocity requirements explain why changing a planet's orbit would require enormous energy. To move Earth closer to the Sun or farther away would demand altering our orbital velocity, either slowing us down or speeding us up by kilometers per second. The kinetic energy involved in moving a planet-sized mass at such speeds exceeds any imaginable power source, ensuring that planetary orbits remain stable against any conceivable natural or artificial perturbation. The precision of these velocities creates the stable solar system we inhabit. Each planet moves at exactly the right speed for its distance, maintaining orbits that persist for billions of years without significant change. Minor variations occur due to gravitational interactions between planets, creating subtle oscillations in orbital parameters. But these fluctuations remain small compared to the overall stability of planetary motion. This stability allowed life to develop on Earth over geological timescales. Had our orbital velocity been significantly different, Earth might have drifted into an unstable orbit, either spiraling toward the Sun or escaping into the outer solar system. The precise balance between velocity and gravity creates a cosmic safe zone where planets can maintain their orbits indefinitely, providing stable environments where complex processes like biological evolution can unfold across billions of years. The orbital velocities we measure today essentially match those that existed when the planets formed, a testament to the stability of gravitational systems and the enduring nature of the cosmic dance that began when our solar system emerged from its primordial cloud. Before modern science revealed the true nature of planetary orbits, ancient civilizations watched in wonder as certain bright objects moved against the fixed background of stars. These wanderers, or planets in Greek, seemed to follow mysterious paths across the celestial sphere, sometimes appearing to reverse direction during retrograde motion. Ancient astronomers painstakingly tracked these movements, developing increasingly sophisticated models to predict planetary positions. The Babylonians, Greeks, and later Islamic astronomers created detailed tables of planetary motion, not understanding orbital mechanics, but accurately describing the patterns they observed. The Babylonians began recording planetary positions as early as 1800 BCE, creating astronomical diaries that tracked the movements of Mercury, Venus, Mars, Jupiter, and Saturn across the night sky. These records served both practical and religious purposes, as celestial events were thought to carry divine significance. Over centuries, Babylonian astronomers accumulated enough data to recognize patterns in planetary motion, allowing them to predict when planets would appear in specific constellations or when they would undergo retrograde motion. Greek astronomers inherited this knowledge and attempted to create geometric models explaining why planets moved as they did. Claudius Ptolemy, working in Alexandria around 150 CE, developed the most sophisticated geocentric model, placing Earth at the center of the universe with planets and moon orbiting in complex paths involving epicycles, circles within circles that attempted to explain retrograde motion and varying planetary speeds. His Almagest compiled centuries of observations into tables that could predict planetary positions years in advance with remarkable accuracy, despite being based on incorrect assumptions about cosmic architecture. The model worked because mathematical patterns can describe motion regardless of whether the underlying theory correctly explains physical reality. Ptolemy's epicycles captured the appearance of planetary motion as seen from Earth, reproducing the patterns without understanding that Earth itself orbits the Sun. The system's complexity, requiring dozens of circular motions to account for all observed planetary behavior, should have suggested that something fundamental remained misunderstood, yet it dominated astronomical thinking for over 1,000 years. Islamic astronomers preserved and expanded this knowledge during medieval times, building observatories and refining planetary tables to greater precision. Scholars like al-Battani and Nasir al-Din al-Tusi made observations and calculations that would later prove crucial to European astronomers, developing heliocentric models. They questioned aspects of Ptolemaic astronomy while creating practical tools for navigation and timekeeping based on planetary motion. The patience required for ancient astronomy staggers modern imagination. Observers spent lifetimes tracking planetary positions night after night, recording measurements by hand, comparing observations across decades to detect subtle patterns. They couldn't photograph the sky or use computers to analyze data, relying entirely on visual observation and manual calculation. Yet through this dedication, they discovered the orbital periods of visible planets with impressive accuracy, measuring timescales ranging from months to decades, using nothing but careful attention to celestial rhythms. Defining a year becomes complex when you leave Earth's familiar 365-day cycle and venture to other worlds in our solar system. On Mercury, a year lasts only 88 days, meaning you could celebrate 4 birthdays in a single Earth year. On Neptune, a single birthday would require waiting 165 Earth years, far longer than any human lifespan. These varying year lengths affect everything from seasonal patterns to how we would measure time if we ever established human presence on other worlds. The concept of a year transforms from a universal measure into a planet-specific phenomenon tied to each world's unique relationship with the Sun. Imagine living on Mars, where each year stretches to 687 Earth days. Your birthday would arrive only slightly more than half as often as it does on Earth. Children would grow nearly twice as old in Earth years before celebrating their next Martian birthday. A 10-year-old on Mars would be approaching 20 in Earth years, creating confusing age comparisons for anyone moving between the two worlds. The situation becomes even more unusual on the gas giants. A person born on Jupiter would wait 12 Earth years to celebrate their first birthday, reaching what we consider adulthood before experiencing their second Jovian New Year. On Saturn, a single year encompasses nearly 3 decades of Earth time, meaning most humans would experience only 2 or 3 Saturnian years across their entire lives. These differences would force future colonists to reconsider how they measure time and mark life's milestones. Would Martian settlers celebrate Earth years to maintain connection with humanity's homeworld, or adopt local years that actually reflect their planet's orbital rhythm? Would children on Jupiter celebrate Earth birthdays to avoid waiting over a decade between parties, or embrace the slower passage of local years? The varying year lengths create fascinating calendar challenges. Earth's calendar divides its 365-day year into 12 months of varying lengths, a system that works reasonably well for our specific orbital period. Mars would require either fewer longer months or more shorter months to subdivide its 687-day year. Neptune's 165 Earth year period defies traditional monthly divisions entirely, as any meaningful subdivision would still span multiple Earth years. Some worlds present additional complications. Venus's year is shorter than its day, creating a situation where the Sun rises and sets less frequently than the planet completes full orbits. Traditional concepts of months and seasons based on solar position become almost meaningless in such an environment. These considerations remain theoretical for now, but they illuminate how deeply our experience of time connects to Earth's specific orbital period. The year feels like a fundamental unit of time because it's marked by recurring seasons and solar positions that have governed human life since our species emerged. On other worlds, time itself would feel different, measured in rhythms alien to human intuition, creating new relationships between consciousness and the cosmic cycles that mark the passage of planetary years. Some planets maintain mathematical relationships in their orbital periods that create gravitational harmonies throughout the solar system. Neptune and Pluto, for instance, orbit in a 3-to-2 resonance, meaning Neptune completes 3 orbits for every 2 of Pluto's, preventing the two worlds from ever colliding despite their crossing orbital paths. These resonances create stable configurations that can persist for billions of years, protected by gravitational interactions that push objects back into alignment whenever they drift slightly out of sync. Understanding orbital resonances reveals hidden order within the apparent chaos of countless objects orbiting the Sun. The Neptune-Pluto resonance ensures that whenever Pluto crosses inside Neptune's orbit during its eccentric journey, Neptune remains far away on the opposite side of the solar system. By the time Neptune circles around to that region of space, Pluto has moved onward in its orbit, maintaining the separation. This choreographed dance has continued for millions of years, and will continue for millions more, the two worlds never approaching closer than about 17 astronomical units, despite their interweaving paths. Jupiter's 4 largest moons demonstrate perhaps the most elegant resonance in the solar system. Ganymede, Europa, and Io orbit in a 1, 2, 4 resonance, meaning that for every orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This precise relationship creates a gravitational rhythm that has remained locked for billions of years, with the moon's mutual gravitational influences maintaining the pattern against perturbations that might otherwise disrupt it. The asteroid belt displays resonances in the form of gaps rather than concentrations. At specific distances from the Sun, where orbital periods create simple ratios, with Jupiter's 12-year orbit, the asteroid belt shows conspicuous empty zones. Asteroids that once occupied these gaps experienced repeated gravitational tugs from Jupiter at the same point in their orbits, gradually nudging them into different paths until the resonant zones cleared completely. These resonances aren't coincidental, but emerge from the mathematics of gravitational interactions playing out over immense timescales. When objects drift into resonant configurations, the gravitational pulls they exchange create feedback mechanisms that either stabilize the resonance or disrupt it entirely. Stable resonances persist while unstable ones dissolve, creating the patterns astronomers observe throughout the solar system. Saturn's rings display countless resonances, with small moons creating gaps and waves through gravitational interactions with ring particles. The Cassini division, the most prominent gap in Saturn's rings, results from a 2-to-1 resonance with the moon Mimas. Ring particles in this region complete 2 orbits for every one of Mimas's, experiencing repeated gravitational tugs that gradually clear the gap. These mathematical harmonies reveal that gravitational systems naturally organize themselves into ordered patterns when given enough time. The solar system has spent 4.5 billion years settling into configurations where resonances either stabilize interactions or clear objects into new orbits, creating the structured architecture we observe today. Orbital eccentricity measures how much an orbit deviates from perfect circularity, ranging from 0 for a perfect circle to nearly 1 for highly elongated ellipses. Earth's orbit has an eccentricity of just 0.017, making it nearly circular, while Mercury's eccentricity of 0.205 creates a much more elliptical path. This eccentricity affects how much a planet's distance from the Sun varies during its orbit, influencing everything from climate patterns to orbital velocities at different points in the journey. Planets with higher eccentricity experience more dramatic variations in the Sun's apparent size and the intensity of solar radiation they receive. Mercury's elliptical orbit creates wild variations in solar heating across its surface. At perihelion, the closest approach to the Sun, Mercury receives roughly 2.3 times more solar energy than at aphelion, its most distant point. Combined with Mercury's slow rotation and lack of atmosphere, this variation contributes to the most extreme temperature range of any planet in the solar system, with daytime temperatures exceeding 430 degrees Celsius, while nighttime temperatures plunge to minus 180 degrees Celsius. Mars displays the second highest eccentricity among the major planets at 0.093. This ellipticity means Mars receives about 45% more sunlight during southern hemisphere summer, which occurs near perihelion, than during northern hemisphere summer near aphelion. This difference drives some of the planet's most dramatic weather patterns, including global dust storms that can engulf the entire world during perihelion approaches when solar heating reaches maximum intensity. The gas giants follow more circular paths despite their immense distances from the Sun. Jupiter's eccentricity of 0.049 and Saturn's 0.056 create only modest variations in solar distance throughout their orbits. Neptune follows the most circular path among the outer planets, with eccentricity of just 0.009, varying less than 1% in distance from the Sun between perihelion and aphelion. Orbital eccentricity directly affects the speed at which planets move through different portions of their orbits. Kepler's second law requires that planets travel faster near perihelion and slower near aphelion, compensating for changing distance to maintain the equal area sweep rule. Mercury's high eccentricity creates speed variations of about 40% between its fastest and slowest orbital motion, while Earth's nearly circular orbit produces speed changes of only about 3%. These eccentricities remain relatively stable over millions of years, though they do vary slowly due to gravitational perturbations from other planets. Earth's orbital eccentricity oscillates between 0.000055 and 0.0679 over a 100,000-year cycle, one of several orbital variations that contribute to Ice Age cycles by affecting the distribution and intensity of solar radiation reaching our planet's surface. Understanding eccentricity helps explain why some worlds experience more variable climates than others, and why orbital predictions require accounting for changing speeds and distances throughout each planetary year. Comets trace some of the most eccentric orbits in the solar system, swooping from the distant Oort cloud down toward the Sun before returning to the frozen outer reaches. Short-period comets like Halley's Comet complete their orbits in decades to centuries, while long-period comets can take millions of years to return to the inner solar system. These icy wanderers demonstrate that orbital periods can span from days to geological ages, depending on the object's distance and the shape of its elliptical path. Comet orbits remind us that the solar system's architecture extends far beyond the familiar planets into realms where objects travel for millennia between solar visits. Halley's Comet follows an elliptical orbit with a period of approximately 76 years, carrying it from just 0.6 astronomical units from the Sun at perihelion out to 35 astronomical units at aphelion, well beyond Neptune's orbit. This means the comet spends most of its time in the frigid outer solar system, only briefly passing through the inner planetary realm, where solar heating vaporizes its ices and creates the spectacular tail visible from Earth. Historical records document Halley's appearances stretching back to 240 BCE, allowing astronomers to trace its orbital history across more than 2 millennia. The orbital eccentricity of comets far exceeds that of any planet. While planetary eccentricities rarely exceed 0.2, comet orbits commonly display eccentricities of 0.9 or higher, creating extremely elongated ellipses. Some comets follow nearly parabolic paths, with eccentricities approaching 1. These objects spend centuries or millennia drifting through the outer solar system before making their brief perihelion passages. Long-period comets arrive from the Oort cloud, a theoretical sphere of icy bodies surrounding the solar system at distances potentially reaching 50,000 to 100,000 astronomical units from the Sun. Objects in the outer Oort cloud move so slowly through space that their orbital periods extend to millions of years. A comet with an orbital period of 1 million years has completed only about 4,500 orbits since the solar system formed, spending most of solar system history in frozen darkness billions of kilometers from the Sun's warmth. Each passage through the inner solar system changes a comet slightly. Solar radiation and heating vaporize surface ices, gradually depleting the comet's volatile materials. Some comets disintegrate entirely after multiple perihelion passages, breaking apart under thermal stress or losing so much mass they cease to produce visible tails. Others get captured by planetary gravity into shorter period orbits, transforming from long-period visitors into regular inhabitants of the inner solar system. Jupiter's gravity particularly influences cometary orbits, occasionally capturing passing comets into orbits that repeatedly bring them through the inner planets. The Jupiter family of comets consists of objects whose orbits have been modified by gravitational encounters with the giant planet, most displaying periods between 5 and 20 years. As planets orbit the Sun, tidal forces create subtle but measurable effects on both the orbiting worlds and the Sun itself. Earth's moon gradually slows our planet's rotation through tidal friction, while simultaneously spiraling away at about 3.8 centimeters per year. Similar processes affect all orbiting bodies, though often on timescales too vast for direct observation. These tidal interactions mean that orbital periods aren't perfectly constant but evolve slowly over millions and billions of years. The solar system we observe today represents a snapshot of an ever-evolving gravitational dance that will continue changing throughout cosmic time. Tidal forces arise whenever gravitational pull varies across an object's diameter. The Moon's gravity pulls more strongly on the side of Earth facing it than on the far side, creating a stretching effect that produces our familiar ocean tides. This tidal bulge doesn't align perfectly with the Moon due to Earth's rotation, creating friction that gradually slows our planet's spin. Each century, Earth's day lengthens by about 1.7 milliseconds. An imperceptible change in human timescales, but significant over geological ages. The energy lost to tidal friction doesn't disappear, but transfers to the Moon's orbit, gradually pushing our satellite farther from Earth. Billions of years ago, the Moon orbited much closer, appearing larger in the sky and creating more dramatic tides. The young Earth rotated faster, with days lasting only 5 or 6 hours. This tidal evolution continues today, slowly but inexorably reshaping the Earth-Moon system as energy transfers from rotational motion to orbital motion. Mercury demonstrates an even more dramatic tidal effect. The Sun's powerful tidal forces on the nearby planet have locked Mercury's rotation into a 3-to-2 resonance with its orbit. The planet rotates 3 times for every 2 orbits, a stable configuration resulting from billions of years of tidal evolution. Mercury's rotation gradually slowed until it reached this resonant state, where tidal forces maintain equilibrium rather than continuing to slow the rotation further. Jupiter's moon Io experiences perhaps the most extreme tidal effects in the solar system. Gravitational pulls from Jupiter and the other Galilean moons constantly squeeze and stretch Io's interior, generating enough heat through tidal friction to power intense volcanic activity. Io's surface constantly renews itself with lava flows, making it the most geologically active body in the solar system, all powered by tidal forces arising from its orbital configuration. These tidal processes operate throughout the solar system, gradually modifying orbital periods and rotational rates over timescales spanning millions to billions of years. The orbital architecture we observe today differs subtly from the configuration that existed when life first emerged on Earth, and will continue evolving slowly throughout the solar system's remaining lifetime. Tidal forces represent the universe's patient hand, reshaping orbital systems through persistent, gentle pressure applied across ages. Each planet's axial tilt combined with its orbital period creates unique seasonal patterns unlike anything we experience on Earth. Mars, with a tilt similar to Earth's, experiences seasons roughly twice as long due to its longer year. Jupiter's minimal axial tilt means it barely has seasons at all, despite its 12-year orbital period. Uranus's extreme tilt creates seasons lasting 21 years each, where one hemisphere experiences decades of continuous sunlight, followed by decades of darkness. Understanding how orbital periods interact with axial tilt reveals the diversity of temporal experiences across our solar system's worlds. Earth's seasons emerge from our 23.5-degree axial tilt, which causes different hemispheres to receive varying amounts of direct sunlight as we circle the Sun. During Northern Hemisphere summer, Earth's North Pole tilts toward the Sun, creating longer days and more intense solar heating. 6 months later, the same hemisphere tilts away, bringing winter's shorter days and weaker sunlight. The 365-day orbital period divides neatly into 4 seasons of roughly 3 months each. A familiar rhythm that has governed agricultural cycles and human activity throughout our history. Mars experiences this same seasonal mechanism, but stretched across its 687-day year. Martian spring lasts about 194 sols, the Martian term for days, while summer extends 178 sols, autumn 142 sols, and winter 154 sols. These extended seasons allow weather patterns to develop more fully than on Earth. Dust storms can persist for months, growing from regional disturbances into planet-wide events that obscure the entire Martian surface. The seasonal cycle of carbon dioxide freezing and sublimating at the poles creates visible changes in Mars's ice caps, expanding and contracting with the passage of Martian years. Venus's minimal axial tilt of just 2.6 degrees means it experiences virtually no seasonal variation, despite its 225-day orbital period. The Sun remains nearly directly over the equator year-round, creating uniform heating conditions across all latitudes. Combined with its dense atmosphere that redistributes heat efficiently, Venus maintains remarkably constant surface temperatures regardless of season or location, a hellish consistency that never varies. Saturn's 26.7-degree tilt creates Earth-like seasonal geometry, but the seasons unfold across its 29.5-year orbital period. Each season lasts more than 7 Earth years, long enough for atmospheric patterns to shift dramatically. Saturn's hexagonal polar vortex, a 6-sided jet stream pattern surrounding the North Pole, changes color with the seasons as atmospheric chemistry responds to decades of varying sunlight. Mercury's minimal 0.034-degree tilt creates essentially no seasons. The Sun tracks nearly along the planet's equator throughout its 88-day year, maintaining consistent solar angles at each latitude. Any temperature variations Mercury experiences result from its eccentric orbit rather than axial tilt, with the entire planet heating and cooling based on distance from the Sun rather than hemispheric seasonal patterns. Planetary orbits remain remarkably stable over millions of years, maintaining their periods with extraordinary consistency despite countless gravitational perturbations from other solar system objects. Computer simulations show that the inner planet's orbits should remain stable for billions of years into the future, though with some gradual evolution in their exact characteristics. This stability emerges from the solar system's particular configuration, where planetary spacing and masses create a gravitationally balanced system. However, chaos theory suggests that predicting exact planetary positions becomes increasingly uncertain when projecting more than about 100 million years into the future. The spacing between planetary orbits creates natural buffers that prevent gravitational interactions from destabilizing the system. Mercury orbits far enough from Venus that the two worlds never approach closely. Earth and Mars maintain sufficient separation that their mutual gravitational influences remain minimal. This architecture emerged naturally during the solar system's formation, when gravitational interactions either stabilized configurations or disrupted them. Jupiter's massive presence actually contributes to inner solar system stability rather than disrupting it. The giant planet's gravity dominates the outer solar system, preventing asteroids and comets from scattering chaotically through the inner planets. While Jupiter does perturb the orbits of inner worlds slightly, these effects remain small and predictable, creating oscillations around stable average values rather than cumulative changes that might destabilize orbits entirely. Yet perfect prediction remains impossible beyond certain time horizons. The solar system exhibits chaotic behavior in the mathematical sense, where tiny uncertainties in current positions and velocities grow exponentially when projected forward in time. An error of 1 millimeter in measuring Earth's current position becomes an error of thousands of kilometers when calculating its position 100 million years hence, making precise long-term predictions fundamentally impossible regardless of computational power. This chaos doesn't mean the solar system will fly apart, only that predicting exact positions far into the future exceeds our capabilities. The orbits remain bounded and stable, even though we cannot calculate precise planetary locations across geological timescales. Think of it like weather prediction. We can confidently say summer will be warmer than winter next year, but cannot predict whether rain will fall on a specific day decades from now. Some scenarios could disrupt orbital stability. A close pass by another star, though extremely unlikely, would gravitationally perturb planetary orbits. A rogue planet entering the solar system from interstellar space could scatter inner worlds into new configurations. Yet, the probability of such events occurring before the Sun exhausts its fuel in 5 billion years remains vanishingly small. The historical stability of Earth's orbit over 4.5 billion years suggests our current configuration represents a particularly robust arrangement. Life evolved across geological ages because orbital stability maintained relatively consistent climate conditions, allowing complex biological processes to unfold without catastrophic disruptions from orbital chaos. The journey to understanding planetary orbits spans thousands of years and countless civilizations. From Babylonian astronomers tracking planetary positions to Newton's universal law of gravitation, Copernicus revolutionized astronomy by placing the Sun at the solar system's center, while Kepler discovered the mathematical laws governing orbital motion. Newton provided the theoretical framework explaining why Kepler's laws work, revealing gravity as the fundamental force orchestrating cosmic dance. Einstein later refined our understanding with general relativity, showing that gravity results from space-time curvature rather than a mysterious force acting at a distance. Nicolaus Copernicus published his heliocentric model in 1543, arguing that Earth and the other planets orbit the Sun rather than everything revolving around Earth. This seemingly simple rearrangement solved numerous problems with geocentric models, particularly explaining retrograde motion naturally as a consequence of Earth overtaking slower outer planets during our respective orbits. Yet Copernicus still assumed circular orbits, requiring complex additions to explain observed planetary positions accurately. Johannes Kepler inherited astronomical observations from Tycho Brahe, whose decades of meticulous measurements provided the most accurate planetary position data ever compiled. Working with Tycho's Mars observations, Kepler spent years attempting to fit circular orbits to the data before finally accepting that planetary paths must be elliptical. This breakthrough led to his 3 laws of planetary motion, published between 1609 and 1619, which described how planets move without explaining why they followed these patterns. Isaac Newton provided the missing explanation in 1687 with his Principia Mathematica, demonstrating that a universal force of gravitation acting between all masses could produce exactly the orbital behavior Kepler had described. Newton showed that elliptical orbits emerge naturally from inverse square gravitational attraction combined with conservation of energy and angular momentum. His laws of motion and gravitation united celestial and terrestrial mechanics, proving that the same physical principles govern falling apples and orbiting planets. Newton's framework dominated physics for over 2 centuries, until Albert Einstein revealed in 1915 that gravity operates through space-time geometry rather than force at a distance. General relativity describes gravity as the warping of space-time by massive objects, with planets following the straightest possible paths through this curved geometry. For most solar system applications, Newton's simpler equations provide sufficient accuracy, but Einstein's theory becomes necessary for extreme gravitational environments or precise measurements like GPS satellite positioning. Each generation of astronomers built upon foundations laid by predecessors, gradually refining humanity's understanding of orbital mechanics. The knowledge we possess today, allowing us to calculate orbital periods with extraordinary precision and predict planetary positions centuries into the future, represents the accumulated wisdom of thousands of years of patient observation, mathematical innovation, and theoretical insight. The orbital periods we've explored tonight emerge from this deep understanding, measurements made possible by centuries of dedicated work seeking to comprehend the cosmic rhythms governing our solar system. Determining where the solar system ends becomes ambiguous when you realize that the Sun's gravitational influence extends incredibly far into space, potentially affecting objects trillions of kilometers away. The Oort cloud, a theoretical sphere of icy bodies surrounding our solar system, could extend halfway to the nearest star, with objects requiring millions of years to complete single orbits. These most distant members of the solar family move so slowly that their orbital velocities approach just meters per second. Understanding these extreme orbital periods reveals that our solar system's boundary isn't a sharp edge, but a gradual fading of solar gravitational influence into interstellar space. The Kuiper belt, extending from Neptune's orbit to roughly 50 astronomical units from the Sun, represents the first major boundary beyond the major planets. Objects here complete orbits in centuries, moving through space at velocities around 4 to 5 kilometers per second. Beyond this region lies the scattered disk, where highly elliptical orbits carry objects between the Kuiper belt and distances exceeding 100 astronomical units, with orbital periods stretching to thousands of years. But the solar system extends far beyond these regions. The Oort cloud potentially surrounds the Sun in a vast spherical shell, beginning around 2,000 astronomical units and possibly extending to 100,000 astronomical units or more. Objects in the inner Oort cloud might complete orbits in hundreds of thousands of years, while those in the outer reaches could require millions of years for a single circuit around the Sun. At such distances, the Sun appears as merely another star, providing no perceptible warmth. Yet these distant objects remain gravitationally bound, slowly circling in the darkness. An object orbiting at 50,000 astronomical units from the Sun would take approximately 11 million years to complete one orbit, traveling at speeds measured in meters per second rather than kilometers. Its motion through space would be imperceptible across human lifetimes, drifting so slowly that centuries would pass before it noticeably changed position against the background stars. Such objects spend their existence in near absolute zero temperatures, frozen remnants from the solar system's formation that have barely moved since the Sun first ignited. The heliopause marks another boundary, where the Sun's influence transitions from dominant to negligible. This is the point where solar wind pressure equals interstellar medium pressure, roughly 120 astronomical units from the Sun. The Voyager spacecraft crossed this threshold, entering interstellar space while still technically orbiting the Sun gravitationally. They've escaped the Sun's immediate particle environment, but remain bound by solar gravity, following orbital paths that will take them thousands of years to complete. Theoretical calculations suggest the Sun's gravitational influence extends to roughly 2 light-years, about halfway to the nearest star. Objects at this distance move so slowly that distinguishing between orbiting and escaping becomes almost meaningless, as the slightest perturbation from passing stars could alter their trajectories. While we focus on how planets orbit the Sun, the entire solar system itself orbits around the Milky Way galaxy's center, completing a circuit approximately every 225 to 250 million years. This galactic year, or cosmic year, means the Sun and all its planets are passengers on an even larger journey through space. Since Earth formed 4.5 billion years ago, our solar system has completed roughly 20 galactic orbits, circling the galaxy while the planets simultaneously orbit the Sun. This nested hierarchy of motion, planets orbiting the Sun orbiting the galaxy, reveals that motion and orbital periods exist at every scale throughout the cosmos. The Sun orbits the galactic center at approximately 220 kilometers per second, carrying Earth and the other planets along in this vast cosmic journey. This velocity dwarfs planetary orbital speeds, yet we perceive no motion, no indication that our entire solar system races through the galaxy at nearly 800,000 kilometers per hour. The distances involved are so immense that the Sun's position relative to nearby stars changes only slightly across human lifetimes, creating the illusion of celestial permanence. During a single galactic year, profound changes occur on Earth. The last time our solar system occupied its current position in the galaxy, dinosaurs roamed the planet during the Triassic period. One galactic year before that, the supercontinent Pangaea was forming. The solar system has witnessed the rise and fall of entire ecosystems, the evolution of countless species, and the transformation of Earth's surface during each 2 to 5 million year circuit. The Milky Way itself rotates differentially, with inner regions completing orbits faster than outer regions, much like planets orbit the Sun at speeds determined by distance. Our solar system occupies a position roughly 26,000 light-years from the galactic center, placing us in a relatively calm suburban region between spiral arms, where star formation proceeds at a moderate pace. This location may have contributed to Earth's habitability, protecting us from the intense radiation and gravitational disturbances common in more crowded galactic neighborhoods. The galaxy's rotation carries us through varying cosmic environments. Sometimes we pass through spiral arms, where star density increases and supernova rates climb. Other times we drift through quieter regions between arms. Some scientists have suggested these galactic environmental variations might correlate with biological events on Earth, though the connections remain speculative and controversial. Even the galaxy itself moves through space, falling toward the Virgo cluster as part of the local group of galaxies. Motion extends to every scale, from electrons orbiting atomic nuclei to galaxy clusters drifting through the expanding universe. Orbital periods measure time across this vast hierarchy, from fractions of seconds for atomic processes to billions of years for galactic motions. The planetary orbital periods we've explored tonight occupy the middle range of this cosmic spectrum, human-scaled rhythms we can observe and measure, connecting us to the fundamental patterns governing motion throughout the universe. We've journeyed through the solar system tonight, measuring time in planetary years that span from Mercury's swift 88-day sprint to Neptune's patient 165-year drift through the outer darkness. Each world marks time according to its distance from the Sun, following mathematical principles that transform gravity and motion into the rhythms we call orbital periods. These aren't abstract numbers, but expressions of cosmic balance. Velocities precisely calibrated to maintain stable orbits across billions of years. Mercury races at 47 kilometers per second, while Neptune glides at just 5.4. Each speed perfectly suited to its distance, each orbit a consequence of fundamental physical laws operating with elegant consistency throughout space and time. We've seen how Kepler discovered the mathematical patterns, how Newton explained the gravitational mechanics, and how Einstein revealed the geometric nature of space-time itself. We've explored orbital resonances that create gravitational harmonies, eccentric orbits that stretch into ellipses, and tidal forces that slowly reshape orbital systems across geological ages. We've ventured to the solar system's edge, where objects take millions of years to complete single circuits, and recognized that even our Sun orbits the galaxy, carrying all its worlds on an even vaster journey. Tonight, as you rest, consider the extraordinary privilege of existing in this particular moment of cosmic history. You're a passenger on Earth, a world that completes its circuit in exactly the time required for seasons to nurture life, positioned at exactly the distance where water remains liquid and complexity can flourish. Our 365-day year has governed every human civilization, every biological rhythm, every cycle of growth and rest since life first emerged. The planets continue their ancient dance, tracing paths they've followed for billions of years, paths they'll maintain long after human memory fades. You're part of this cosmic clockwork, connected to orbital rhythms that extend from atomic scales to galactic distances. Rest now, held safely by Earth's gravity as we circle our star together, marking time in the gentle rhythm of planetary motion. Sleep well,